Let's get started. Welcome, everyone. This is the short course for software for AI on HPC. And my name is Zhenhua He, and I'm an associate research scientist at Texas A&M High Performance Research Computing. My background is in geoscience and computer science. I do numerical modeling and machine learning, especially in computer vision. So today I will be teaching the short course, and also my colleague Richard Lawrence. He will be teaching a part about the containers. He's our resident container expert. So Richard, could you please introduce yourself a little bit?
Howdy, my name is Richard Lawrence. I'm a user support specialist in the High Performance Research Computing Group. I will be teaching containers for use with mainly Python, and I can also help with most of the other tasks we'll be doing today.
Thank you, Richard. Let's move on. And first, we want to introduce a little bit about high-performance computing. High-performance computing, or HPC, refers to the use of supercomputers or clusters of high-performance machines to solve complex computational problems. We know that nowadays we have very computational intensive numerical simulation or AI ML projects, models. And so we need these supercomputing clusters to help us. And also there are features of HPC, including the parallel computing. For example, you can run across many processors to run your job in parallel. And also on HPC clusters, there could be some specialized hardware accelerators, such as GPUs, TPUs, IPUs. Here, when I say IPU, I mean intelligence processing unit. Maybe someone has never heard about this before. And also it has a scalable architecture, so you can scale, add computational resources to your workloads, and then it can run faster. So why HPC is important for AI here? Because today we want to talk about software for AI, right? Because AI ML, we know that for today, the AI ML models has gone to a situation that the model size is growing so large, and also the data set is huge. And then, so we need a lot of computing resources for training or inference of these for these models. HPC could provide some of the necessary infrastructure to accelerate AI training and inference. For example, on our ACES computing cluster, we have accelerators such as NVIDIA GPUs, and also we have some other Intel data center GPUs as well, and also specialized hardware accelerators such as GraphCore intelligence processing units. And also HPC provided the necessary high-speed storage and interconnects to handle the large data sets you use. Now the data sets could go to terabyte and even bigger. So, and also the HPC can have optimized resource utilization by using the Slurm workload manager. So I will talk a little bit about Slurm, how it manages the computer resources, and also enable your research at a scale. Any questions so far? Okay, let's get an overview of the computer resources hosted at Texas A&M High Performance Research Computing. we operate 5 computing clusters, Grace, Vital, Launch, Faster, and ACES. If you are interested in more information about all these clusters and you can see this page, I hope you can still see my web page. I think I shared this. So you can see our resources here. And today we are mainly focused on the ACES and ACES actually. So we have 5 different computing clusters. Launch is mainly for regional computing. I think it's a Dell cluster, AMD EPYC Genova processor, and NVIDIA A30 GPUs. For the ACES, is also a Dell cluster, and it has different types of accelerators. Here you can see it has Intel data center GPUs, Intel FPGAs, NVIDIA H100 A30s, and NEC vector engines, NAS silicon coprocessors, and also the graphical IPUs as well. Faster is also a composable cluster. I haven't talked about this yet. ACES and Faster are 2 composable clusters we have here. And Faster, the GPU accelerators are mainly NVIDIA GPUs. You can see A100, A10, A30, A40, and T4. Grace is dedicated for Texas A&M University. So if you are a Texas A&M researcher, you can use Grace. And I think we have about 100 GPU nodes on Grace. So it has about 1,000 nodes in total. Vital, it provides a secure and compliant computing environments, and also it supports both Windows and a Linux operating system. So this is the 5 computing clusters we have here. Today we will mainly focus on ACES, but Faster and ACES are 2 composable clusters we have. I will be explain more about the composability a little later. Yes, here. So what is composable HPC architecture? So we have been heard about common or traditional HPC layout for a long time. It's built on converged hardware, and its hardware design is static, means like if you have, for example, on that compute node, you have fixed amount of like GPU, memory, and it's very hard to move all these components around to other compute nodes. So it's very static and not flexible. However, for composable HPC, it's built on disaggregated hardware. So this hardware will be in different pools of resources. For example, the GPUs can be in GPU pool, and then when you need a certain amount of GPUs, you can use some technology, for example, composable fabrics, and to pull the needed GPUs onto a node, and then you can compose a node. So this is the difference between composable. I think we have another figure showing the difference about traditional layout and a composable layout. For example, in here, I would take this one for example. For example, we have 4 GPUs dedicated to this compute node. However, if one user, for example, he used 1 GPU and all the CPUs on this compute node, other users would not be able to use the GPUs on this node anymore. So it's a complete waste of computing resources, especially when we know that the GPUs are very expensive. However, in composable layout, the GPUs will be in a pool of GPU, and then by using the liquid composable fabric, and we can pull the GPUs to compose a node. For example, back to here, if these 3 GPUs that haven't been used, we can pull these 3 GPUs and to compose another node, and then other users can use the nodes as well. So it's very it's a kind of like an optimization of resource usage in a data center. So we do a lot of we do some benchmark research on this liquid composability as well. So if you're interested, you can check our papers on the benchmarking composable infrastructure. Okay, let's move on. As I said, we have 2 composable clusters at Texas A&M HPRC. We have Faster is our first large-scale composable CPU GPU platform, and the GPUs are mainly NVIDIA GPUs. So it's not very complicated, but for ACES, it's the composability is for mixed resources workflows. It's like we have NVIDIA GPUs, Intel data center GPUs, and also other accelerators as well. So it's a mixed resource and also complicated than the faster cluster. So we will focus on ACES today. Okay, I want to talk about a little bit about the status of the composability today. Our composability is currently handled by system administrators. So for users, you cannot like just use some JavaScript to compose a node of your to satisfy your need. But you can always contact us to request a given composable configuration for a cluster. For example, you want to have a node with for example 4 NVIDIA A100 H100 GPUs. You can let us know, and we will try our best to accommodate your needs. And you can do some research or profiling or benchmarking or some your AI ML research. And then once our system administrators compose the node, they will tell you the partition name in the queue, and then you can just specify the partition name in your Slurm job file. I will talk about a little bit about Slurm later as well, and then you can use the GPUs on the node. Integrating the Slurm and the liquid software stack to handle the composable configurations automatically is still in progress. So we needed to tackle some technical difficulties and then to make it work. Here we also have some other accelerators. As I said, the intelligence processing units, ANC vector engines, they cannot be composed because of the software and incompatibility with Slurm. So we currently they are not composed. Okay, any questions now? Okay, let's move on. I will give a ACES overview now. So ACES stands for Accelerating Computing for Emerging Sciences, and it's a National Science Foundation funded. So the project mission is to, it's a ASF, ACSS program's cyber infrastructure testbed. It offers a accelerator testbed for numerical simulations and AI ML workloads. So that's why we have a variety, many different types of accelerators on this testbed. So if you want to test any of these accelerators, you can contact us, and then we can get you on the cluster, and then you can run your workflow on the accelerators that you want. And also we provide consulting, technical guidance, and training to researchers to use different technologies. And we have been hosting tutorials and workshops in conferences and short courses like this one to help researchers to use different accelerators. And also we have help desk. And if you have any questions, you can send your questions to us, and then we will help you from there as well. And also, we welcome collaboration on computational and data-enabled research. For example, we have been collaborating with many HPC centers and universities to do some benchmarking work, for example, either on the composable technologies or the AI ML accelerators as well. We benchmark the performance, and we benchmark the different configurations of the cluster as well. So if you have any workflows you think you can that can be used to benchmark different accelerators or composability, you can contact us. And I will be showing I will show the contact email at the end. Okay, this is the ACES. The ACES pictures is hosted at Vesta Campus Data Center at Texas A&M University. And this is the ACES computing cluster. The pictures from different angles. So I think. Okay, this is about the configuration of ACES now. And we can see it has some 15 development hosts and 4 management nodes, data transfer nodes as well, 3 logging nodes for the cluster, and a 2.54 petabyte cluster system. And also, if we move down, and you can see we have some Sapphire Rapid nodes. And for this part, they are mainly PCIe Gen 4 composable fabrics. So they compose the Intel PVC GPUs and NetSilicon coprocessor, Intel FPGAs, B2R FPGAs as well. And you can also see we have Optane SSDs. These can be adjustable as memory as well. So if your application or your research workflow needs a large memory, we can try to use the Optane SSDs as the memory, so to make your research workflow work on the node. And this part is mainly the PCIe Gen 5 composable fabrics. It composes like Intel PVC GPUs, NVIDIA H100 GPUs, so they are on PCIe Gen 5 fabric. And also, we have other configurations as well. I will maybe, for the communication of the GPUs, for example, we have configurations, and we will talk about this later. Okay. And here, on the top corner here, top right corner, we have several standalone nodes as well. As I said, these NEC vector engines and the graphical IPUs, they are not composed. So they are standalone nodes. And you can see we have a GraphCore Bow IPUs, and it has 16 IPUs there. And also we have a GraphCore Colossus IPU pod 16. And it's also a standalone node. So here is the ACES system description. We have Sapphire Rapid nodes, 110 compute nodes. And also we have some Ice Lake logging and management nodes. These are the number of nodes for on PCIe Gen 4 composable fabric, 16 nodes on PCIe Gen 5 composable fabrics, 110 nodes using the NVIDIA Infinite Band interconnect. So 2.5 petabyte storage. Here's I have introduced most of these accelerators. So you can see the numbers as well. And we have about 30 NVIDIA H100 GPUs on ACES and 4 NVIDIA 830 GPUs. And we have a lot of Intel data center GPUs. We have about 120 Intel data center GPUs, max 1100. So if you are interested in any of these accelerators, you can contact us and then we can collaborate to make your workflow work on the accelerator. Okay, next is about accessing ACES. So since we have rich resources, how can we access the ACES? I think most of you guys today is on our training allocation. So you should have no problem to access the ACES computing cluster. Let's look at the steps. First, let's go to the Texas High Performance Research Computing website. And from there, you can see the top, the top right corner, there's a portal menu. In the menu, there's ACES portal access. So that's where you should click on to get to the ACES Open On Demand portal. ACES portal is the web-based user interface for ACES computing cluster. We use Open On Demand portal. It's an advanced web-based graphical interface framework for HPC clusters. So I guess many HPC clusters use Open On Demand portal. Maybe some of you guys are familiar with this already. And also we have HPRC portal YouTube tutorials on the slide. You can click on this if you want to learn more about our portal. And then after that, I guess most of guys have the access, your access ID and your access password. So once you click on the portal, ACES portal access, you will be directed to this page. For access users, you are it's good to use this one, Access CI, Exceed, or you can choose your university or home institution, and then to use your authentication from there. So here, you will need to put your access ID and access password and then login. That will go through the dual authentication. So after that, we will be on the ACES Open On Demand portal. And after that, we will click the clusters tab and then click underscore ACES shell access. We will be open terminal in your web browser. So after that, you should see terminal. And in the prompt, you will see the login node. For example, the number of, for example, here, I see login node number 1. So let's do that and get you guys on ACES computing cluster. So I will just search in my search bar. I will search terminal HPRC, and the first one will be our web page. And here you will see the portal menu. So I will click on ACES portal access. Now I'm on the access cilogon.org, and I will be able to select an identity provider. I can choose either Access CI, Exceed, or I can choose Texas A&M University. And but I will use the Access CI, Exceed. If I click on log on, and then I have saved my access ID and a password here. So you can see I didn't type. And then after you type your access ID and the password, you can click on login. So it will ask you to check for a dual push. And I have the dual push to my phone now. And then on my phone, I have the dual app, and then I just click on the approve button. it will let me open the ACES on-demand portal now. So if you have any questions or problems, you can let us know, and then we will try to let you land on the ACES Open On-Demand portal. So I will give a minute or two, and you will see some messages and from Texas A&M University High Performance Research Computing about our consulting. This is our help desk email, so you can always send your questions to our help desk and our website, knowledge base pages, and a YouTube channel, and also some policy information as well. Okay, thank you. Actually, now we will be now you can see I'm not on I'm on login node 3 now. Can you guys tell me which login node you are on now? So as I said, we have some NVIDIA GPUs on ACES computing cluster. We have A30 GPUs, but A30 GPUs is computing power is not so it's not so powerful, so it supports less intensive workflow for some numerical simulations and AI ML models. So mainly it's with the inference. And for NVIDIA, we also have 30 NVIDIA H100 GPUs. So it is computing powerful. So it supports intensive workloads. For example, some very computing intensive numerical simulations and AI ML model training. So it can be you can try to use the H100 GPUs as well. So how can you use these NVIDIA accelerators? So they are in a Slurm partition called GPU. So you will put this line into your Slurm job file, and also put a generic resource, the dash grass, and you can put GPU. For example, if you want to use the A30, you put the A30 in the to replace this GPU type, and you can replace the number as well. For example, you want to use 4 or A30s, or if you want to use H100 GPUs, you can replace this with the H100 and then put the number of the H100 GPUs that you want to use. And also we have about 120 Intel data center max GPU 1100. So it can be used for AI model training or inference. And in our in the Slurm partition, its name is PVC. PVC stands for I think it's a quantitative vacuum. PVC, and then in the grass argument, you need to put a GPU, comma PVC, comma the number of PVC that you want to use. For example, you want to use 8 or 6 or 4. You can specify the number of the PVC GPUs here. And also we have a command utility to show you the PVC node features. For example, you can, as I said, we have different composable fabrics. For example, Gen 4 composable fabrics, Gen 5 composable fabrics, and some of the nodes even have X-Link bridges. That's Intel X-Link bridges for GPU communications. So that could speed up the communication among the GPUs. So some of the nodes have 4-way X-Link bridges. Some of the nodes have 2-way X-Link link bridges. So you can test this as well. We do some work on this benchmarking, and we find it can speed up the communication among the PVC GPUs. And also currently we plan a PVC training event on March the 4th. For today, because we mainly provide a high-level overview of ACES computing clusters and the software for AI on ACES, and then so we will not go deeper into every accelerators and software. So we mainly give you a very high level overview. So you can click on the link and register for example, the PVC training, and in that training we will teach you how to run deep learning models on the PVC GPUs and how to migrate the PyTorch or TensorFlow models to PVC GPUs as well. So that will be covered more on the PVC GPUs. And also next accelerators for AI is GraphCore IPUs. IPU stands for Intelligence Processing Units. So here a diagram shows the comparison between among the IPU, CPU, and GPU. You can see their architecture are very different. And for the IPUs, you can see very small pieces, like the arithmetic logic units has been divided into many smaller units, and these units are called tiles. And each tile has its local distributed memory, so it can be very each tile can use this to prepare its own constructions, and also it's a MIMD called multi-instruction, multi-data, so multiple data. So it's very good for fine-grained parallelism. We have done some benchmark on IPUs and compared it with the GPUs as well. We find that for very smaller batch sizes, the IPUs can achieve a very high throughput. So compared to GPUs, of course, on GPUs, because its memory is here is bigger than the IPU. So when the batch sizes go higher, the GPUs can reach high throughput. But for the IPU advantage is it's good for fine-grained parallelism and some other grouped operations like grouped normalization or convolution, and it has some advantages as well. So especially for some applications that uses smaller batch sizes. So if you are interested, you can also let us know, and we can share our paper to you as well. These are the documentation of GraphCore IPUs. This page shows how you can convert your model, for example, the TensorFlow model to IPU model. So it will do several steps, and then you can run the model on the IPUs. And also, because as I said before, the GraphCore IPUs are standalone nodes. They are not composable yet. They are not composed yet. So you can, when you are on the logging nodes, you can do SSH Poplar 1 or Poplar 2 to get onto the IPU machines. But if someone has tried this, you may get an error because you haven't been given access yet. If you want to use our IPU, contact us at help@hprc.tmu.edu, and we will give you the access, and then you will be able to run SSH Poplar 1, which has the Colossus IPU, and also you can do SSH Poplar 2, which has the Bow IPUs. Bow IPUs is more advanced than the Colossus IPU, so you can try both as well. So when you need to use the SDK, the IPUs, you need to enable the GraphCore SDK environment, software development kit. So we have our knowledge base pages for both classless and bow IPUs, and you can run some examples on these accelerators. After you enable the SDKs, you can type GC monitor. So this is very like NVIDIA SMI. You can check your processes on which IPU, and then things like that. And also some other, it tells you the IPU machine address, serial number, software versions, the type, the IDs, and the local numbers. And also we have planned a IPU training event as well. Here's the link. If you want to learn more about GraphCore IPUs and want to see if your application is suitable for IPUs or not, and you can join us on March the 18th. So we will go much deeper on the IPUs. I will teach you how to run the machine learning, different machine learning frameworks on IPUs, and converting the code to IPUs. And also we will try to do some model replication and model pipelining. Model replication means like your model can be replicated to different IPUs, multiple IPUs, and then these models can run in parallel. For model pipelining, is when your model is very large, one IPU cannot accommodate the large model, and then we can partition the model into several stages, and then we can put the different stages onto different IPUs, and then we can run them as well. So if you're interested in knowing more about the IPU training event, well, please click on the link, and then we can register. And also, this is about the ACES system software stack. And so I think this is more from our system administrators. And so we use ASCAD for cluster management. Our OS is Red Hat Enterprise Linux. And we use Slurm for scheduling. And our storage is Elaster, and also we use L mode to manage the softwares on our cluster. Use EasyBuild for building softwares. The web portal, as I said, we use the Open on Demand portal. We also use Globus for data transfer, for transferring data. OpenXD mod for job reporting. So this is about the system software. Okay. Now you have got on the ACES computing cluster. So how can you run your AI machine learning models on the ACES computing cluster? So first you will have to set up your environment, right? So and then run your AI machine learning models in the environment. And first one, I want to introduce the L mode module system. So you can use the software that has been built on our cluster. And on our ACES cluster, we have about like 2,400 software modules. Of course, it's the number of unique software packages is about 740. Most of the softwares have multiple versions. Yeah, and then if we go to the page, okay, I think I can just click on here, and then now you can see the software modules on ACES. For example, here, okay, I cannot find the search bar now. How about we go to the faster? Faster is our first composable cluster. So yeah, I found the search box here. So for example, if you want to search what PyTorch modules on this is faster cluster, for example, you can see Volt Torch, and the GPyTorch, OpenFold. These are all torch-related modules that exist on ACES clusters. So you can find all this. If you use TensorFlow, you can search TensorFlow as well, and you can find all this TensorFlow-related modules. Okay, so if you find your modules on the cluster that has already been built, so how can you use them? Actually, we have a knowledge base for our software modules. So if you click on here, it will tells you how to find the software on the cluster. For example, you can use module avail, or you can use module spider, FMQ. There are some examples as well. I think I will give an example later as well. So each version of software application library is available as a module. The module names have this type of format. And so you will see the software name. For example, you want to load PyTorch into your environment, and you can search PyTorch, and then it has a version number, and also this one, PyTorch was built with the CUDA 12.1.1. So you will see the CUDA version as well if you want to use the GPU. And also, actually, if you just module load this PyTorch in the environment, it will not let you do that. It will give you an error because this software depend on other tool chains as well. Tool chain is a collection of tools that help build the software. So okay, for here, we know that the module system is a hierarchical. So the software could be built on other softwares. So when you do this, you can do module spider, PyTorch this, the version CUDA 12.1.1. You will find its dependencies, and then first load the dependencies, and then load the PyTorch, and the software you want. And then so next one will be some examples. So you can use module avail. It can list all the available modules on the cluster. You can imagine that will be slow, right? So you can navigate using spacebar or arrows or J and K. You can quit with Q, but also you can use MLA, and this can save the results to a file. For example, here, module spider Python, you can find the Python versions existing on the cluster as well. So, and then after you find the modules you want, and then you can use module load and the software. Sometimes I just copy and paste the software, the name here, and then it will be loaded. And then you can use module list to see what modules have been loaded in your current session environment, and then you will be able to use them. Module purge after, for example, after one project you work on another project, the other project may use different versions of software. You want to use module purge to unload all modules, so it doesn't affect the workflow of the next project. So here is a hands-on exercises since you are on ACES, so you can use these commands. And for example, MLA PyTorch, and then you can module load the select one version. I select the one that with CUDA, and then if you want to directly module load this PyTorch, it will give you an error. So you cannot do that yet. So you can use module spider, PyTorch, and you will find the dependencies of this module, and then you can put the dependencies in this yellow box and followed by the PyTorch module, and that will allow you to load the modules. And then you can do module list. This is a short abbreviation for module or module load. So it can do different things. ML can either can be interpreted as module or module load. So if you load another, for example, this PyTorch depends on a different version of GCC. If you load another one, the message will show you, hey, the GCC version will be changed to another version. And then you can do the module list again, and then remove all the loaded modules. So let's do it together. Okay, my session has been terminated. Or I have this one. Okay, so it's been terminated. And then MLA, PyTorch. So you can see a list of PyTorch modules. If I directly want to module load, for example, I want to load this one. I just copy and paste, so I don't want to type. It tells you how mode has detected the following error. So the modules exist, but cannot be loaded as requested. So it tells you try module spider. And then, so I'll just copy and paste a module spider. And now it tells you more information. You will need to load all modules on any of the lines below before the PyTorch module is available to load. So we can do that. And for example, it depends on GCC and Open MPI. Just copy and paste, and then also the software module, PyTorch, and then let it load. Okay, now it should be loaded in the session now. If you use module less or just simply ML, you will see all the loaded modules. You can see here there are many other modules as well, but we can check PyTorch. Yeah, we have the PyTorch CUDA. We also have the GCC 12.3 and OpenMPI and all this. So after you load this, you should be able to run some PyTorch workloads. So that's the software built on our cluster by our system administrators. For example, we want to load a different version of software, GCC 10.2. We have GCC 12.3. If you want to load this, it will tell you some information here. For example, here, due to module path changes, the following has been reloaded if the version changed. For example, your GCC has been changed, the version has been changed. Some related modules also has been changed. So this is about this. Okay, next will be our Python virtual environment and a Conda environment and even containers. I think I will give a 5 minutes break, and then we will come back at about 11, and then we will continue with the Python virtual environment, Conda environment, and containers. Okay, welcome back, everyone. Let's continue. And of course, besides using our software modules, you can create your own Python virtual environment as well. So it's more flexible, and I know there are your research maybe depend on a version that does not exist on our cluster, and we don't have it on as a software modules. So you can install that into your virtual environment. So that's also okay. And a Python virtual environment is an isolated environment where you can install packages without affecting the system-wide Python installation, right? So for our Pythons, this is not a complete list of the Pythons that we have. Actually, we also have Intel optimized Python as well. So if you are interested in loading the Python and then create a Python virtual environment, you are welcome to use the Python as well. So for example, here, I give an example about creating a Python virtual environment. So first, you can see it's always a good practice to do module purge before you load any other software modules, because there might be some existing software modules in your environment already. So do a module purge can give you a clean environment, and then you can module load other software modules. For example, here I loaded the Intel Python, so 2024. This is for a project about Intel data center GPUs. So I just borrowed that slide and put it here. So you can use Python VM module, and then give the Python give the environment name. And then you can activate the virtual environment and then install the dependencies into the environment. So this was for Intel PVC GPUs. I will also introduce this in the PVC training short course as well. So you can, for example, you can install this into your environment. Of course, we don't have these. I think we don't have these modules available on our cluster. So it's good to install these packages into your virtual environment. And the next one will be Conda management system. You can use Conda as well. Conda is an open source package manager and an environment management system that help you install, manage, and deploy software packages. We have mini Conda and Anaconda on the cluster, different versions. And mini Conda is pretty lightweight, and Anaconda has the full distribution with many pre-installed packages. So if you want to, you can choose either one, lightweight mini Conda or more abundant Anaconda or something like that. And we have different versions as well. You can use the module load command, module spider, to find either mini Conda or Anaconda, and then you can load the version that you want. After that, for example, here I load an Anaconda 3, 2024.2, and then I kind of create a AI Labs virtual environment, and then activate this environment, and then use Conda install, and then after that we do source the activity. So you can do this as well on the cluster. Next will be my colleague Richard Lawrence talking about the containers, and also Richard, are you available now to talk about the containers?
Howdy, I'm Richard. I'm here to tell you about containers. And in particular, I'm going to show an example of how we can use containers to help with AI activities. So what I'm showing you here is a very small subset of my training curricula. I generally teach multiple training courses per semester that are dedicated just for containers. So here are the 3 container courses that I taught in fall, for example, fundamentals of containers, and then two variants of containers for scientific workflows, each targeting a different container runtime. If you want to know more about containers, you can find the recorded videos for these on our YouTube channel, or you can sign up for the next time that I teach them, which I believe will be in April. So I would like to tell you what a container is. A container is a process that has its own view of local resources. So there are many local resources, file system, user IDs, networks, devices. For this example, we're focusing on the file system as the resource that the process has its own view of. So I'm representing the process with a gear symbol, and I'm representing the file system with this compact disk graphic. So a normal process is able to read files from the file system anywhere on the file system that it has permission to read. But within the file system, there may be a sector that itself is a representation of a complete file system. We call that an image. And it's possible to have a process that sees just the image as though the image were a real file system and does not see the rest of the physical file system. That is the main use case for containers. Why do you want a container to see a subset of the file system? Well, it's because when you're installing software into the global file system, you may not have permission to do that, but you may have permission to install software into a subset of the file system. And then if your container sees that subset as the whole file system, it is as though you installed the software into the global space as far as that process knows. So why do we use containers? Well, we're scientists, so we want to know how this is going to help us do science. Containers are shareable because you can upload a container image and use images shared by others. Containers are portable because you can bundle all the libraries you need to run on a computer with a given architecture. So an architecture might be the x86-64. A different architecture would be ARM. That's the class of CPUs. Within a given class of CPUs, all the Linux kernels are compatible with the containers. So that is a very wide variety of machines you can run on with any given container image. And finally, reproducibility. If your software is in a container, then you don't care so much what happens to the cluster environment. It's really unlikely that the cluster administrators are going to be changing the CPU architecture, and anything else they do, your container process probably won't even notice. So if you need to reproduce your science at a later date, you're confident that you'll be able to do that. So there are many container runtimes. So here's a sample of some container runtimes. There are three that we have on ACES, which are Docker, Singularity, and Charlie Cloud. Although we have Docker on ACES, I am not able to make it do anything useful because Docker was not designed for shared HPC clusters. Docker was designed for personal desktops. So it lacks some features that are needed to be useful for HPC. The two runtimes that we have that are really useful on HPC are Singularity and Charlie Cloud. They're very similar. The main point of them is that they understand how to work with the high performance hardware, so they won't get in the way of your program using the GPUs, using multiple nodes, using the network file system. Whatever your program needs to use, it can still do that. I will be showing an example of Singularity today. But first, we need to know where container images come from. So if you're doing machine learning, probably you would like to use Python, because a very high number of machine learning libraries are written in Python. So here's one, which is PyTorch. PyTorch accelerates machine learning with GPUs. So who knows better how to build GPU accelerated software than the GPU vendor itself? We have NVIDIA GPUs on ACES. So this is where I go to get containers full of software for NVIDIA GPUs. I go to the NVIDIA Container Registry. The NVIDIA Container Registry has a lot of software that's pre-assembled for use with NVIDIA GPUs, including PyTorch, which is a popular Python machine learning library. I'm sure we've already talked about. So if we download this container image, we should be able to use it to do PyTorch-based applications with the NVIDIA GPUs. So this is the URL to this specific container image, and it's a family of container images that are tagged. So they update the software, they update the tag. It's kind of like software versioning, but it's more of a date-based thing because they don't just have one software in there. It's an entire software stack. So what's in the container can be very complicated. Hopefully the tag is at least human readable. In this case, it will be human readable. So I have selected a particular tag from the web page, which was 25.01-py3. And now I need to convert the name of the container image into the syntax I need to fetch it from the command line. So we have our knowledge base, and that's a link here to our knowledge base. The knowledge base explains how you build this syntax for fetching that image from the internet. So I'll click on it in just a moment so we can see. So if you have a URL, then you use the URL and you use the recipe to turn that into a Singularity pull command. But I've already done that for this example. So for this example, what do we need to know? We need to be on a compute node, and then we need to set up a few variables. And then we have the command which fetches the image from the repository, Singularity pull, the name of the file where you'd like to save it, and then this URL-like string that tells Singularity where to find that image on the internet. Finally, whenever you're ready to launch an application, like a Python script, you just need to prefix your command with Singularity exec and the name of the image. This will launch your process, but your process will see the image as the file system instead of seeing the real physical file system. So when you go Python script, if script wants to import PyTorch, it will start searching around in the image to see if it can find PyTorch. And it will be able to because it's installed in the global space in the image. So I will demo this for you quickly. I have a command prompt over here. I just need to get on a compute node. So that I'm going to use srun to interactively get to a compute node. There's more than one way to get to a compute node. I need to specify a time. What's that? Dash time equals 60 minutes or something. I need some memory. Let's say 10 gigabytes. I need some cores. Let's say 8 cores. And I need to be on a node that has a GPU. And right now there's a node in the GPU debug partition that I checked was available a few minutes ago. So I'm going to try to get on that node. And to have an interactive session, I'm doing -pty-i. This is not the only way to get to a compute node. It's just the one that I'm doing right now because this is what I saw that there was a node available. In general, you can get to a compute node by your favorite method. Like you could open up Jupyter Lab on a compute node and use that. Is this not going to work for me? Did I make a mistake? I think I probably made a mistake because that should be working.
Do you need to specify the GRAS since you are?
I could try that.
I see the GPU the H100 GPU debug node is free now.
Okay, that was it. I needed to ask for a GPU. So now I'm on a compute node. How do I know? Host name, AC098. That's a compute node. Does it have GPUs? It does. I don't actually need the GPUs right now. I just need to be on a compute node. So now I'll go back to my slide and I'll grab my code. So what I'm doing is I'm setting up some variables. Web proxy allows me to reach the internet. Singularity needs a place to put some temporary files. And then we can pull this. But be careful, it has to be all in one line, which is probably not going to work because when you copy and paste, of course, there's always stray characters. Okay. So we've got some progress bars on the screen. They're flashing like they're trying to make me crazy, but I do think they are making progress. Last time I pulled this image, it took about a minute. It's not small. It's medium. This is normal. It takes about a minute to fetch an image, and about half that time is Singularity just packaging up those files into the Singularity image format. So on the command line, I specified that I would like to save the image in a file named pytorch25.sif. SIF is the Singularity image format. It packs all the files in the image into one file. That's good for high performance computing because it's efficient to read one large file over a network. And since all our compute nodes are connected to each other over a network, we don't want to slow the file system or the network down by reading thousands of little files. So that is why we use a single file format. But it does take Singularity about a minute to pack up all those files into that single file format.
I can continue, and then after like 10 minutes or so, we can come back and see the container image, and then you can do the example. So next we will talk about the software we use on the ACES computing cluster. We use Slurm to managing the computing resources and scheduling the requested resources to your workloads. So it's like as we have done, you have your laptop and then you connect to a logging node, either 1, 2, or 3, and then behind this, when you on the logging node, you will do like write your code and test your code, debug your code, and then after that, you are confident that like, hey, I can let the job run a compute node now. So don't waste the two of your service units or credits. And then that will go through the job scheduler. The Slurm will schedule your job onto a node or a few nodes. For example, you want to run your job across many nodes. That's also okay. And we have hundreds of more compute nodes here. And then, so on the logging nodes, it's mainly for some lightweight workloads. So you don't want to run a large, very computational intensive job there. So if you're, that's mainly for on the compute nodes. So, and then this is a Slurm JavaScript example. And then you can see, you can specify, actually Richard just do a S run, and then it's very similar. And the arguments are here, dash dash time, dash dash n tasks per node, CPUs per task, memory, and graphs. If you want to use the GPUs, you can specify the GPUs here and also specify the partition. You can specify the output directories or arrow directories, and then you can module load the modules in your job file as well, and then you can use your GPU command. So there are two types of GPUs on ACES computing nodes, H100 and A30. So, for example, the max value for the number can be changed since our ACES computing cluster is a composable cluster. For example, sometimes we can, yeah, of course you can, if you do a single node, sometimes we can compose like, I think for H100, I used like 16 H100 on one node. So I specify 16 here for a single node job. Of course, you can do jobs, run jobs across nodes. You can specify, hey, I want to run with the 30 H100 GPUs. You can put it here, but most of the time our H100 GPUs are busy. So your job could be delayed, and then it could be after some other people's smaller request. For example, they may just request a one H100 there. So try your best to estimate your computer resource needs, and then put the best number here. Next is our portal job composers. We know that ASF Access or NAIR platform, and then we have a lot of AI researchers, and they have different levels of HPC experience. Some of them have very extensive experience in HPC, and they know what they are doing, and then they can just get on our clusters. But some of them lack HPC experience, so they don't know how to write a Slurm job file, and then they need help on this. They don't want to spend time learning all this. So we kind of develop some tools to help these AI researchers, so they don't have to, they can focus on their AI research or algorithms or things like that. And then for here, we have a Jonah, a tool called Jonah framework, Jonah Composer or Jonah job listing and a job composer. And this can help you create job scripts and the Slurm job scripts and monitor your jobs. And then so they can make their life easier. For here, there are some screenshots for the Jonah Composer GUI. For example, here, they can just specify the job name and the location and the environment. For example, they can select customizable environments for their workflows. For example, they can choose either Python, R, or some other AI environment as well. Like Richard, we have saved some container images, and then I have put the some of this in the environment list as well. But it's not public yet. I will just show how it works. History of previous, and you can also see the history of your previously submitted jobs. Um, here are some more. So introduction about the environment, and you can also add modules here as well. So this is just simply a form that helps some AI researchers with the no to little experience, HPC experience, so they can just run their jobs. So this will be this is the generated Slurm job file, and then they can just submit it, and then, or if they needed to add some more commands, and then they can just add their commands in this editable window, so they can just click submit, and then the job will be submitted to the cluster compute nodes. And also for AI and ML, we also have some environment for the AI researchers, but now these for Intel GPU container and NVIDIA GPU container, these are not public yet. So we will make this public as soon as possible, and then so some AI researchers just use these containers, use these environments. So I will show a quick demo as well here. So for here, I will just use the Jonah Composer. So for example, if I want to run a test on Intel PVC GPUs, you can see this kind of like blue. So it's not public yet. So you may not have this list in your environment list. We will make this public as well. I want to choose the Intel PyTorch container, and then add modules. No, for example, number of cores, maybe just one, number of nodes, maybe just one. I want to use the Intel PVC GPUs, total memory. So for example, I maybe just 5, and I want to run it out for 1 hour. And then accounts, you can leave it blank. It will use your default account and additional. And then we can do preview. You can see actually I put a demo script. But of course, if you know your own script here, you can just delete it. I just let it run a demo. So you can click submit. And then this portal ACES will tell you you have submitted a bad job. It's okay. And then also here, you will see the PVC test as well. The job ID and even the location. You can just click the location, and then you can see the output file and all this script, because I had a classification model for demo. I think this one, let me check. So you will be able to see the training process for the demo AI model. So it will tell you the all this here. So it's still in development, our Jonah Composer. So stay tuned, and we will try our best to make it make life easier for some AI researchers without a lot of HPC experience. And also we know there are a lot of popular model distribution strategies like data parallel, distributed data parallel, sharded data parallel, tensor parallelism, and pipeline parallelism for PyTorch, and mirror strategy or multi-worker mirror strategy for TensorFlow or something. Yeah, these strategies can get your workflow across multiple GPUs or even across multiple nodes. And you can try this on our clusters as well. I think in this afternoon, I have another short course called AI Tech Labs. I even put a sample script for distributed data parallel that can run across multiple GPUs. If you are interested. Richard, do you want to show your container PyTorch? You run it, and then
Still
I
not
can stop
ready.
here for a few minutes.
It's
not ready.
not ready.
Okay, I will continue then. So because on ACES clusters, we have some hardwares, for example, Intel. We know that NVIDIA GPUs is pretty standard and everybody run their workflows on NVIDIA GPUs, but for Intel, they also have data center GPUs as well, and then they develop some tools for the developers to develop some applications on Intel hardware as well. So they have Intel One API toolkits built on their base toolkit. They also have AI analytics toolkit for machine learning, data science pipelines, and here we also use. I think we have modules for Intel AI analytics toolkit on our cluster as well. But one thing is the Intel seems to has removed their channel on Conda. So when they try to install something, then we might give you error. But we are trying to try to find a workaround for that. And also, but you can also use the Intel AI tools selector. For example, if you want to run your AI model on the Intel GPUs, you can go to this link and then select AI tools. You can see customize, and then use the pip install, or you can see the Python version. For example, here I choose PyTorch. It will give you a command to install with the pip, and also the versions are guaranteed to match, and so this will be much easier for yourself to find the different versions of PyTorch or TensorFlow, and even they have the one CCL, that's the communication library for Intel hardware, and also the hard world is for distribution, is the distribution framework as well. So this is an easy tool for you to start your AI model on Intel hardware as well. So for Graph Core, because we also have intelligence processing units on ACES cluster, and they also have their own develop their software stack for developers to develop the software on IPUs. So you can see the drivers, their popular SDK, and the software development toolkit, and also they have a communication library as well. Some other compiler engine and libraries as well. So they support TensorFlow, PyTorch, Keras, and so on, so many. So if you want, as I mentioned, if you want to learn about the IPUs, we have IPU training tutorials, and I will tell you more about. This is just a software for AI using GraphCore intelligence processing units, and also for besides this, and also they developed Pop Vision tools. Pop Vision tools is a visualization tools for you to visualize your the performance of your program on the hardware. For example, the Pop Vision Graph Analyzer will tell you the memory usage throughout the lifetime of your program. For example, if you check the profile, and then you can see for example, you can see a large spike of memory usage. You can click on that large memory spike, and then you will see which operation or which layer of your AI model use that much memory, and then you can optimize it, right? So and also they developed a system analyzer as well. This mainly for you to identify some bottlenecks between the host system and the IPU devices. And so this is what for GraphCore intelligence processing units. If you are interested in try your applications on GraphCore IPUs, I welcome you to attend our training. These are the popular SDK. Just some how to activate them. And also on ACES, we know that Hugging Face Hub has been an important platform for machine learning models and datasets. So we try to facilitate the access to Hugging Face on ACES as well. So we even built some model for Hugging Face Hub. So you can just module load the Hugging Face Hub, and then you can do something from there. For example, and also we have Git FS for different versions. So you can download the large files like the machine learning model weights and the data sets. So for example, here I show an example of the Video Llama, which is a vision language model, and then you can download these pre-trained model weights.
Hugging Face libraries, the transformers for the pre-trained models. For example, you want to fine-tune some pre-trained model, you can use this as well here. Just to give an example here. Performance monitor and optimization. I want to check with Richard again if he's ready. Richard, do you think your container is ready for a demo now?
No, it still isn't. I was very wrong.
Sorry, I cannot hear you. Maybe my AirPods died. I'm sorry, my AirPods died.
No, my container's still not ready.
I just speaker. Okay. Okay. Can you guys still hear me? I'm not using my AirPods, so give me a thumbs up if you can still hear me. So we will continue with the performance monitor and optimization. Okay. Thank you, Andrew. When you run your AI machine learning models, you always want to, for example, on the GPUs, you always want to know, hey, how my model is utilizing the GPUs. So they have actually different tools developed by the vendors. For example, the NVIDIA, Intel, or GraphCore, they have their utility tools that you can use to check the memory usage or the GPU utilization. For example, sometimes you have some memory usage but zero GPU utilization. That might tell you, hey, there's something wrong there because you are not using the GPUs. So you can use this system management interface or utilities to check the accelerator's usage. The first one is for NVIDIA SMI for NVIDIA GPUs. So you can see an interface like this one. And I was on NVIDIA A30 GPUs, but it's the same for other GPUs as well. And you can see I run an AI job on 2 GPUs. And XPU MCLI and SISMA is for Intel PVCs. I didn't do a screenshot here, but you can go to our knowledge base page and you can see the SISMA and the XPU MCLI, what they will output. For example, you can use XPU MCLI dump. For example, if you specify some matrix, for example, GPU utilization, GPU core temperature, or memory temperature, you can opt all this. Once we have done some research on the thermal throttling of accelerators, we use this utility tool to output the temperature of the accelerators, and then we plot them, and then we see how the temperature will be varying during the model running. So that will be help you to do some research as well. And the GC monitor is for GraphCore IPUs. I have it. So this is I think I have showed this, a part of this. And for example, when you use the GC monitor, you will see your processes here, and also to show which IPUs your processes are using. So, and even the temperature, power usage, and something else also be showing on this as well. So some software for some specialized hardware. We want to introduce them to you on ACES. And also, if you want to really do some like profiling and debugging of your AI machine learning program, and for example, on NVIDIA GPUs, you can use the NVIDIA Insight, right? So you can either download the NVIDIA Insight on your local computer and then download the profiling files from the host and then you can then use the NVIDIA Insight to read the file, and then it will show a screenshot, show you usage of the graphical interface like this one. So for example, you will need to put some NVTX in your code to track the for profiling. And for this one, for example, we set the number of workers to be 0. And then for data loading process, it will use the main Python process. And then so it will become very busy. And then sometimes the data loading, you will see, for example, your steps, your AI model steps, they will have a big steps between these steps, a gap for here. If you use NVIDIA Insight, you will see this. And even you can enlarge these parts and to see how the time is being utilized for example, for some CUDA kernels or things like that. And after that, for example, hey, I found there is a large gap here. I want to try a different number of workers. For example, 1, 2, 4, until, for example, you don't have a large gap. And then, so that will be, for example, when they try number of workers to be 4, the gap is become, they are very, very close to each other now. So they will be not a waste of time, right? So more efficient. This is for NVIDIA Insight. And also you can use TensorBoard for machine learning experiments. So it can help you to track the metrics like your model loss, accuracy, learning rate over time. And also you can check your computational graph. Histograms is for the weight distributions and activations. And even look at some samples for dataset, embeddings or hyperparameter tuning or profiling, monitor the GPU and CPU usage, memory, and bottlenecks. So actually on our ACES portal, we also have TensorBoard. You can open this, and when you run your AI machine learning model, and then you can specify the logs directory, and then for here, when you open the TensorBoard, you can also copy the logs directory into this, and then you open the TensorBoard. You will be seeing something like this one, and you will be able to see the accuracy, loss change, and also some of the histogram or graphs as well, computational graph as well. So, and also, as I said, I didn't include everything here, performance monitor and optimization, because we also have, for example, the graphical IPUs, they have pop vision, graph analyzer, and also system analyzer as well. So you can use that to debug and profiling as well for your AI machine learning models on graphical IPUs. So that's pretty much I want to cover. Richard, do you think you are ready for the demo?
Nope. It is still thinking.
Okay, I understand. Sometimes pulling and packaging the container on HPCs takes some time.
Maybe I should have asked for more CPU cores.
Yeah, when you said 1 minute, I was thinking, wow, what did they do to speed up the process? Because when I did this before, it take about 1 hour, I think, for PyTorch and TensorFlow containers. I don't know. So I will continue. Maybe we will. Yeah, we have as Richard said, we have a container knowledge base as well, knowledge base page as well. You are welcome to our knowledge base HPRC to our knowledge base I think container somewhere. Oh, Charlie Cloud. I don't know if we have a container page or Singularity. Oh, okay. And for example, here we have the knowledge base as well. If you want to learn more about the containers, you can go to our knowledge base. I think we even have a examples here. The Hello World image is not big, so definitely. But for NVIDIA containers, PyTorch or TensorFlow containers, it could take some time to for pulling and packaging on the HPC clusters. So I will continue then. Here is for needing help. So this is our ACES user guide and a faster user guide. If you we have examples to get you started on these clusters. If you want to request, for example, to install some software on ACES cluster, you can always use our ACES portal dashboard, and then you will see a button called request software. And then our system administrators will help you to install the software on our cluster as well. So need help. This is just a hint about to help. You can tell us which cluster, for example, either faster or ACES, your username, job ID, and your location of job file, things like that. Also, we welcome you to take our short course survey, so we can improve for future. Of course, you can do this now. I also want to show you some other helpful resources as well. We have some knowledge base pages for you to get started, and then these are the knowledge base for example, here in this figure, you can see we have user guide knowledge base page. If you click on Intel PVC GPUs or graphical IPUs, that tells you how to set up the environment and how to use how to run some AI machine learning models on these accelerators, and also tells you how to use for example, the profiling tools, things like that. And actually, we try to put everything on our knowledge base page, so some researchers can just go to our knowledge base page and then learn from there as well. And this is our YouTube channel, and we have posted many short videos. This short course will also be posted on our YouTube channel as well. If you missed something, you can go to our YouTube channel and to learn as well. We have many short videos, and including the containers as well. So this is about again, the PVC training and the IPU training. So if you are interested in testing the different accelerators, besides the NVIDIA GPUs, you can register for PVC GPUs and IPUs. This is about getting started on ACES cluster. This is some usage policies. Of course, now I think most of you guys are on our training allocation. If you are interested in using our ACES computing cluster and faster cluster for your AI research, you can always apply for some allocation on your own. For example, for either on Access or Nair pilot, you can create an account and then select the opportunity. For example, for different types of allocations, they have different type of allocations with a different number of credits. And then you can request allocation, receive the credits, and then you can exchange credits onto ACES or faster, and then you will be able to use our cluster and the accelerators as well. So this is in the slides we have how you can apply application for ACES, and so we hope this can help you. This is about some allocation opportunities. Currently, we support 3 different types of accelerations, allocations. The first one is called Explore, the second one called Discover, and the third one is called Accelerate. And you can see they have different requirements for the allocations. The Explorer is the smallest allocation, so it just requires an overview of your project. For Discover, it requires a 1-page proposal, and for Accelerate allocation type, it requires 3-page maximum proposal. So it's kind of like if you want more computing credits, you will have to write a little bit more. So I think, okay, I have the dashboard here. I think I have to talk about the dashboard, some utilities as well on our ACES on Open On Demand portal. If you want to check virtual environment available or environment available, you want to use our shared environment, you can click on this utilities and find what environments are shared, or I think I can do that. Utilities here, for example, you can do GPU avail, and it tells you the availability of the GPUs, and also the node count, configuration of the nodes. Go back to the utilities. For example, if I check the virtual env, so it tells you there is a Intel Python shared environment called Intel AI Python env, and maybe the env's availability. It has more environment for either AI labs, cyber training, and some other environments that I don't know, Intel AI, PyTorch, TensorFlow, and you can check all this. You can, because it's in the shared directory, so you can use that in your Jupyter notebook as well. So Jupyter Helmo. Okay, I think that's all for today. I'll go to my slides. So yeah, we just want to give you this short course to just give you a very high level overview of ACES cluster and the software for AI machine learning. If you guys have any more questions, you can always go back to the slides here. Email your question to our help desk, and we will receive your message, and we will help you from there. Any more questions? Or Richard, if you are, I think it's fine because I know it takes time. It took time for the container to work. Okay, I guess I will stop here, and thank you everyone for attending this short course. And I hope to see you on our ACES cluster to run your AI machine learning workloads. And if you have any software questions or hardware questions, please let us know. And we will try our best to help you and accommodate your request as well, if you want to compose the nodes or something like that. we'll try our best to help you. Thank you. Oh, I see a question in the chat. Anna asked whether if Richard has any slides that he can walk you guys through. And yes, we have I want to show you guys here. For containers, for you guys who are interested in containers, you can always go to our webpage for courses. And I think, can I search containers?
It'll be under previous courses.
Okay, yeah, that's under previous courses. And then containers. So you can see fundamentals of containers, containers for scientific workflows. These fundamental of containers will be happening on April the 1st. So stay tuned, and we will send out the announcement for registering. And so container.
Can you click the view details?
Yes.
I think the student would like to see that the previous slides are here.
Yes. And you can.
So
This is Singularity and Charlie
So I
Cloud.
taught that in the fall, and the slides can be found on our website if you
Yes.
wish to review what I taught in the fall.
And I hope you find this, and I think I can put this in the chat. So where's the so I will put this link to the chat. So hope Anna can find this, and you, if you are interested in the containers, and you can of course you can read the slides here. And also, even our YouTube channel, we have the containers short courses video as well. So stop sharing and also end the Zoom now. Bye, everyone.